Dear learner, I am Soibal Manna. In this video lecture series, I will teach you MATLAB programs related to classical control system, a subject studied in the B.Tech undergraduate program. Throughout this lecture series, I will commence with the basics of the control systems and demonstrate their implementation in MATLAB software. Therefore, this video serves as an introduction to the series. I am now sharing the roadmap for this particular lecture series. Okay, so in the introduction section, first we try to implement Laplace transform in the MATLAB. So this lecture is particularly focused on the MATLAB based on the control system. So in the Laplace transform, first we convert function in the time domain to the S domain in MATLAB. In case of the inverse Laplace transform, we convert function in the S domain to T domain, and in the third section, that is the partial fraction expansion, basically we are doing the partial fraction by using pen and paper, but in the MATLAB it is very easy. Just put your command and you will easily get your partial fraction. From the partial fraction you can easily find the time domain response by using the inverse Laplace transform. Okay, now coming to the second chapter, that is based on the transfer function. So first of all, we in the MATLAB we see how we can present the transfer function in the MATLAB. Then we find zero and pole of a transfer function in MATLAB. Then we plot the zero and pole maps of a particular transfer function in the MATLAB. And next we talk about the series, cascade, parallel and feedback connections in the MATLAB. And in this section, I will be discussing how the time domain analysis can be analyzed using MATLAB. Okay, so in the time domain analysis, we start with the MATLAB description of standard second order system. So in the time domain analysis, we basically use the standard second order system, that is omega n square divided by a square plus 2 zeta omega ns plus omega n square. Okay, then we use the step response of a system, then we use the impulse response of the system, then we talk about the ramp response of the system, and next we talk about the any arbitrary input of the system and their performance. So here you can see performance indices for the response of a system, means from the graph we have to find the delay time, rise time, peak time, maximum overshoot as well as the settling time. Next we talk about the steady state error from the transfer function of a system. Next, we determine the unit step response of any transfer function and find the performance index like delay time, rise time, peak time, overshoot and settling time. And you have to remember the step response of system can be obtained if the system is represented either the transfer function or we can represent it the state space model. Here I also show you about the single input single output system as well as the multi input multi output system, that is MIMO system. Now in this section I present the MATLAB approach to the generation of root locus plots and finding relevant information from the root locus plot. So first we start with the root locus plot using transfer function of the system, then determination of the gain value k at a given point in the root locus, and last we talk about the root locus plotting using state space representation of the system. All are happened in the MATLAB environment. And in this section, plotting of Bode plot in the MATLAB and determination of frequency domain specification for Bode plot in MATLAB are discussed. So here you can see Bode plot for a plotting of Bode plot for a system. Next we try to find the frequency domain specification from the Bode plot in the MATLAB environment. Now here are the two variations is there. If the system is presented in transfer function model, from there we also find the Bode plot, and if the system is presented in the state space model, then also we can plot the Bode plot by in the MATLAB environment. So in the state space model, initially we consider the SISO system, means single input single output. Also we take here one example that is based on multi-input multi-output system. Now we also plot the polar plot in the MATLAB environment. Now coming to the Nyquist plot. So in the Nyquist plot we also plot the Nyquist for the system, and here also we take two presentation. One is basically from the how we can plot Nyquist plot from the transfer function model in the MATLAB environment, and also we plot Nyquist plots in the state space model. So here we also consider two cases. One is for the single input single output system, and one is the MIMO system, that is the multi input multi output system. Then we talk about the designing of the compensator using MATLAB. So here we design the lag compensator by using root locus or Bode plot technique. So here we also see the response before the compensation technique and the after compensation technique through the MATLAB. Then we design the lead compensator, then we design the lead lag compensator. And finally, in case of the classical control system, we talk about the state space analysis of the control system. So all the programming will be done in the MATLAB environment. So first we will start the conversion of the state space model to transfer function and transfer function model to state space model. Then we write the program to find the state transition matrix. Okay, in conventional we generally use the pen paper and use the formula to find the state transition matrix. For in the MATLAB there we use only one single command so that we can easily find the state transition matrix, and it will save your time. Next, to determine the controllability and observability of the system, so we take one state space model and we try to find out whether the system is controllable or not, whether the system is observable or not. If you try to use your formula and pen on paper and pen, it will take lots of time, but the MATLAB, it gives you the result in a fraction of second. Next, we determine the time response of the system, and last we will find the eigenvalue from the state space model. Okay, so thank you. So in the next video I will begin with the Laplace transform. Stay tuned by subscribe my YouTube channel. Thank you.